Okay, let's take a look at 13.4. Back to one of our favorite topics, infinity. So we're going to look at limits at infinity and limits of sequences. Why they spend so much time telling you the same thing. All right, so let's look at this rather curious function here, where f of x is equal to x squared minus 1 over x squared plus 1. Now the denominator being the sum of perfect squares, it can't be factored. So there are no common factors to reduce here. So how do we treat this? Well, if we go back to where we started with this chapter here, doing some substitution, try different values, see what happens. As x becomes larger and larger, the difference between the numerator and the denominator gets smaller and smaller. Okay, so obviously we can put in 0, and that's okay. We don't get an undefined value here. If we put in 1, we get 0. As a matter of fact, if you put in -1, you also get 0. So with the table that you see there in the lower left, they're putting the plus or minus because, again, it doesn't matter if you substitute 5 or -5. The first thing you're going to do is square it and get 25 regardless. So it'll be 24 over 26 for both 5 and -5. And you'll note there as we go through, okay, 5, then we put in 10, then we put in 50, then we put in 100, we put in 1,000. What's happening? Okay, as x grows larger and larger, the values of the function get closer and closer to 1. In fact, it seems like we can make the values of f of x as close as we like to 1 if, depending upon what degree of accuracy you want, just by taking a value of x that's big enough. So this situation here is symbolically. Now again, small details here. It's the limit as x approaches infinity. Okay, everything before we've seen a specific value. So here we have, well, again, you can't plug in infinity. It's not a number, it's an idea. But we saw there from the graph and we saw from the table, as x gets sufficiently large, the limit of this is equal to 1. Let f be a function defined by some interval from a to infinity, then the limit as x approaches infinity is equal to L means we can make that function go as close as we want to L by taking an x value that's big enough. And again, here's our notation. F of x approaches L as x approaches infinity, and nobody ever uses that. Now watch, you'll go off to college and that's what your professor will use. Again, it's not a number, you can't substitute. Oh look, there's different ways of reading it. The limit as x approaches infinity is L. The limit of f of x as x becomes infinite is L. Oh, and here's this one. Fancy wordage. As x increases without bound. Isn't that nice? Um, again, we could go to positive infinity to the right. We could go to negative infinity to the left. And the symbols get so small, you got to pay attention. All right, so here's our limit at negative infinity to go along with our limit at infinity that we had before. Yeah. And when y is equal to L, again, that's our limit value, it's a horizontal asymptote if both the limit to positive infinity and the limit to negative infinity are the same value. Again, we saw that with the graph here of that first example. All right, so find the limit as x approaches infinity of 1 over x, and the limit as x approaches negative infinity of 1 over x. All right, well, what happens when you put in really, really big numbers? 1 over 100, gee, that's 0.01 because, place value, 1 over 1 million, 0.000001. You can make 1 over x as close to 0 as you want by picking a really big value of x. So we can say the limit as x approaches infinity of 1 over x is equal to 0. Put in a really, really big negative number. And again, be careful here. Negative 0.00000001 is pretty much equal to 0. Okay? Please don't tell me that you were going to put down negative 0. Please don't tell me that. No, Hayek, I said don't tell me that. All right, so yay, our lovely little graph here. It doesn't matter if we're approaching positive infinity going off to the right, negative infinity going off to the left. There is a horizontal asymptote. Oh, by the way, we call that a parabola. Sorry, a hyperbola. But, one of the easy ones. So if we go back all the way to law 6, limit of a power, 1 over k to the x, doesn't matter if we're going to positive or negative infinity. Again, just 1 over that constant, k to the 5th power, k to the negative 17th, whatever k is, the limit of that reciprocal function is always going to be 0. All right. Use numerical and graphical methods to find the limit as x approaches negative infinity of e to the x. Hopefully you do remember the value for e. It's a very important, very useful number. Y is equal to e to the x. You can see there in figure 7. Again, anything to the 0 power is 1, so it goes through the point 0, 1. And of course, e to the first, 2.7182818828. You can't graph that exactly there. So the limit of the function here as x approaches negative infinity. Okay, again, it's an exponential function here. Our base is something greater than 1. As we go to the right, it gets infinitely large. But as we go to the left, it gets closer and closer. Again, the x-axis is a horizontal asymptote. So the limit of this function as x approaches negative infinity is 0. Again, there's no way that you can take a value for x, take 2.7 Andrew Jackson squared, raise it to some power, and have that positive number base turn into a negative value. Just can't happen. All right, so for the next one, hold on. It's our old friend sine function. The limit as x approaches infinity of sine of x. You remember this. Please tell me you remember this. Okay, all right, good job that time. Um, it's a periodic function. It's cyclical. It oscillates between positive 1 and negative 1 and positive 1 and negative 1 infinitely. It does not approach any one single value. So yes, the limit as x approaches positive infinity of sine of x does not exist. Yay, everybody cheers for a DNE. All right, so let's go back to, again, what we talked about with sequences. A sequence has a limit L. If it does, then as the number of terms heads towards infinity, the value of a term is equal to that limit. So hopefully you remember back to what we talked about there about convergent sequences and divergent Again, the only difference here between what we just said about any particular function, for a sequence, the value for n has to be an integer. Okay, we can talk about the 20th term, the 2000th term. We can't substitute 4.2 in place of n. Since we know that the limit as x approaches infinity of 1 over x to the k is 0, okay, we looked at that just a little bit earlier here. The limit as n approaches infinity of 1 over n to the k is also 0. All right, so let's take a look at this lovely sequence here. We have an explicit formula for any term a sub n. It's going to be equal to 15 over n cubed times the quantity n times n plus 1 times the quantity 2n plus 1 all over 6. My goodness, what an interesting expression that is. Yeah, that needs some work. Okay, let's simplify the expression because n to the third is n times n times n. For our denominator, we can write that out as a product of 4 terms. Our numerator has 4 terms. Well, let's write it out and let's pair those things up. Okay, so we'll put the 15 over the 6. We're using the commutative property of multiplication. We're just rearranging, and then we can take that n inside the brackets in the numerator and pair that with one of the n's from n cubed. Take that first set of parentheses, put it over in another n, and take that last set of parentheses and put that over the last n. All right, now let's simplify. 15 over 6 reduces to 5 over 2. N divided by n is 1. And now we don't like fractions. N plus 1 over n, we'll split that into 2 terms. N over n plus 1 over n. And then 2 over n plus 1 over n. Again, we'll split that into 2 terms. 2n over n, that's just 2, plus 1 over n. All right. Yeah, we were able to reduce some of it here. I'm hoping that you're in agreement that compared to this original one here, down here at the bottom, it's a little bit more spread out, but it's definitely simpler. All right, so if we use some of our rules here about limits, we can say the limit as n approaches infinity of this expression is the limit then of our simplified expression. The 5 halves, we can pull that out front. And again, the product, we can take the limit of each of those sets of parentheses individually. And again, remember that the limit as n approaches infinity of the 1 over n in both of these cases here, that becomes 0. So this becomes 1 plus 0, which is just the 1. This becomes 2 plus 0, so that becomes the 2. And then the arithmetic is really, really simple. The limit of this sequence as n approaches infinity is 5. And that's it. Okay? So you're looking for these types of problems here to simplify it and get that magical 1 over n, and we know the limit as it approaches infinity is going to be 0, making an easy substitution, easy solution. Well, that didn't take too long. Hopefully the assignment won't either. Good luck.